Section 5.2 is verifying trig identities. Not a lot of procedural stuff that you can just follow. Like if we were solving for theta or something like that. These are pretty much all varying and different looking identities. And you'll kind of have to find a way to do each one, but there's multiple paths you can take to do each one. Let me jump into the first example. And you can see the different methods that they have for verifying trig identity. So basically, they're going to give you an equation, two sides that are equal, and we have to prove that one side is equal to the other side. Okay, so it's kind of like if they said tangent is equal to sine over cosine. Now show it, right? Like prove it by working on one side and making it look like the other side. Here we're going to verify secant of theta squared minus 1 over secant squared of theta is equal to sine of theta squared. Okay, and basically what you have to do is you're going to pick one side to work on. Most of the time this will work. You'll pick one side. Usually you want to pick the more complicated side to work on, and then make it look like the other side. But for the most part, we're only going to touch one side and then make it look like the other side. So in this case, the left side looks much more complicated than the right side. So that means it'll be kind of easier to do stuff to it. And we're going to try to make it look like the right side. That way we can know that, both sides are actually equal to sine squared. That they are the same thing. Now on these identities, they're always going to give you true statements. So it's never going to be like a trick. So really the work that we want to see here is all the middle part till you get to the end, okay? Because technically there is no answer, right? You're just kind of doing calculations that show that both sides are equal. In this case, we would say, okay, well, secant squared minus 1, that's actually equal to tangent squared from the Pythagorean theorems. So we would say, okay, I'm going to change this to tangent of squared on the top, and I'm going to rewrite my secant squared under that. And then we could say, secant squared is actually the reciprocal of cosine squared, right? So because secant squared is in the bottom, I can actually bring it up if I change it to cosine squared. Does that make sense? So it's like changing secant to 1 over cosine, but because it's in the denominator, it's going to go flip up, and it's going to become it's going to go in the numerator. So this will become tangent will still be up there, but now secant will flip up and multiply tangent squared as cosine squared. Okay, and then you're kind of looking to see where we're headed. So we're trying to get to sine squared, right? So then because we're here right now, we know that we can convert this to something that has sine in it. So we'll try that, sine over cosine. These are squared. So that is sine squared over cosine squared times, and we still have cosine squared next to it. And then of course, these are being multiplied, so we have a cosine squared on top, cosine squared on the bottom. We can see that these are going to divide out. and I'm going to be left with sine squared. Okay, and we see that we end up with the same thing that was on the right side. Okay, so on these problems, the part that's being graded is this part, right? This kind of work until we get to the end. Okay? That looks like the other side. And that's how all of these are going to go. But obviously, they can throw anything at you, so there's going to be a million different ways you can approach each identity. Example 2. So these ones that we're practicing, you might never see them again, right? Because there's so many examples of this. But it's really just for you to see the different ways that we can get there. Example 2, verify. This is going to be 2 secant squared of alpha equals 1 over 1 minus sine of alpha plus 1 over 1 plus sine of alpha. Which side do you think is the more complicated, left or right? Yeah, right is definitely more complicated. It has addition, right, between two terms, and it has fractions also. So we'll start on working on the right side only. So because we have a sum of two fractions, what we're going to do is let's actually add them. And one easy way we can add them is by getting a common denominator, just by multiplying the two denominators that are there, right? So let's say I'm going to multiply these two denominators. So we're working on the right side. Try to make it look like the left side. And then on the top, it's going to be, we're going to kind of cross multiply, right? That's how we add two fractions. So it'll be the denominator from the second fraction times the numerator of the top for the first fraction, and then the denominator of the first fraction times the numerator of the second fraction on top. So here we'll have 1 times 1 plus sine of alpha. So this is going to be 1 plus sine of alpha. And then we have plus, and then 1 times 1 minus sine of alpha. So that's going to be 1 minus sine of alpha. On the top, because we're just adding those two terms, we can technically drop the parentheses, right? There's not going to be any sort of sign change or anything, because we're not multiplying by any negatives. So these parentheses that are on top, I don't need, since we're just adding those two things. Okay. And we can start simplifying a bit, right? We can see that we have a positive sine alpha and a negative sine alpha in the numerator. I have 1 plus 1, so we'll have 2 on top. And then on the bottom, right now, if I multiply these, because it's a difference of, think of it like a difference of squares. Then we have x squared minus 9 and it's x minus 3, x plus 3. This is kind of similar. 1 minus sine, 1 plus sine. So this is going to give us 1 minus sine squared. When we multiply that out, okay. And the hint here is that we have a sine right now, right? It's really the only trig function we have, but it is squared, and there is a 1 in there, so maybe we can do Pythagorean theorem right in here. So 1 minus sine squared is actually equal to cosine squared, good, of alpha. And we're getting closer, right? Because we're trying to get to secant. And of course, cosine is the reciprocal of secant, so all we gotta do is convert this to secant. So 2 over 1 over secant squared, but because it's in the denominator, it's gonna flip up and get placed in the numerator. Next to the 2. So think of it like this. Like that. And we showed that that right side is indeed equal to that left side. Example 3, verify. This is tangent of x squared plus 1, close parentheses, times cosine squared x minus 1 is equal to negative tangent squared of x. So definitely the left side looks more complicated. So we'll work on the left side. In this case, because we see that we have these 2 factors, tangent squared plus 1 and then cosine squared minus 1. It kind of looks like we could apply the Pythagorean theorem to each one. So we will want to do that first. That way we can hopefully simplify this into one term, right? And this into one term, and then we'll multiply them if we need to. Tangent squared plus 1, what do you think that would give us? Secant squared. So this one becomes secant squared. And then cosine squared minus 1 becomes we write this one on the side here. We know that this plus this equals 1, right? We want cosine minus 1, so that means I would have to move this over here and move this over here. So cosine squared minus 1 is equal to cosine squared minus 1 negative sine squared. So we'll put negative sine squared over here. Like that. We're trying to, and then we can take a look where we're headed, right? Because it kind of helps. Otherwise, we're kind of going blindly. We're trying to get to the tangent. We have a sine right now. We could use a cosine, right? Because sine or cosine is a tangent. We don't have cosine, but we do have secant. So we can convert this to one of those and then put those together. So you have 1 over cosine times negative sine will give us negative sine squared over cosine squared. And then, of course, this is just negative tangent squared. So the left side is indeed equal to the right side. Okay. So a lot of times you'll kind of get through these by converting what you see into sines and cosines usually. Usually those are the kind of the more basic building blocks, and once you have most of the stuff converted into sines and cosines, whatever you can convert to sines and cosines, then you can work from there. And then obviously when you see things that are squared, usually you'll want to look to see if you can do some sort of Pythagorean theorem application there. Let's see. Let's do 4, but let's do part B. Part B is verify that tangent of x plus cotangent of x is equal to secant of x times cosecant of x. So here the more complicated side would be the left side because we have 2 terms that are being added, right? Addition is a little more complicated than multiplication in trig. So we'll work on the left side. So let's try that trick, right? Let's try to convert everything we can to sine cosine. So tangent we know is sine over cosine. And cotangent we know is the reciprocal of that, right? Cosine over sine. So we're adding these 2 fractions. Let's get a common denominator. If I multiply the 2 denominators, that can be a common denominator. And then, of course, here I have to multiply this by sine, right, to get this. So it's times sine, so we've got sine squared on the top. And then on the other one we have cosine squared. Let me write this here next to it. So we get that. And then, of course, sine squared plus cosine squared is 1. One over sine times cosine. We're trying to get to secant and cosecant, right? And we're actually pretty close. If you notice, we have 1 over cosine, that's secant. 1 over sine, that's cosecant, right? So all we got to do is break this up into 2 products. same fraction, just into two factors here. And then, of course, 1 over cosine is secant, and 1 over sine is cosecant. Secant of x plus tangent of x equals cosine over 1 minus sine. We'll work on the right side here, since it is a fraction. So the way we can work with this, we have this and this, right? There's no, well, notice first, this is already in terms of sine and cosine, right? And also there's no square terms, so there's no Pythagorean theorem that we can apply here or here, right? So then where else can we go? Because we have two terms in the denominator, what we can do is work with this denominator, 1 minus sine. We can multiply by the conjugate, and this is what this looks like. So the conjugate of the bottom would be 1 plus sine, but I would multiply on both the top and the bottom, because that way we're only multiplying by 1, right? So we're not changing this. So this is just equal to 1. So anything times 1 is going to be the same thing, right? So we're not really doing anything extreme here. But we're seeing how we can make it look different so that we can apply more stuff that we have, right? More definitions that we have in our formula sheet. So this will give me, should I multiply this out? Yeah, let's multiply it out on both top and bottom. Cosine times 1, and then cosine times sine. Looks something like that on top. And then on the bottom I have a difference of two terms. One is 1 minus, the other one is 1 plus. So this is going to be 1 minus sine squared. Okay. Pythagorean identity. So now we have a sine squared and the 1 in there floating around. So we will know that 1 minus sine squared will be cosine squared. So let me rewrite the top. And then replace the bottom with cosine squared. If you notice, we're trying to get to secant and tangent, right? But notice that there is a sum between them. So this is a sum of two terms. So we want to find a way to break this up into two terms so we can kind of head in that direction. We do have a sum here. So I'm going to do this fraction and this fraction. Break it up into two fractions. So this is going to be cosine over cosine squared plus sine cosine over cosine squared. Then reduce each one. The first one will be 1 over cosine. The second one will be sine over cosine. So this one of those cancels, and this cancels. And this one, we lose that one, and one of these. And of course, 1 over cosine is secant, plus, and then we have tangent. Okay, any questions so far?
Why did you decide to work on the right side? And how would you know which side to work on?
Technically, you can choose any side. It's just that usually the more complicated side is a little easier to do more work on it. Trying to get that mosquito. But in this case, the right side is technically more complicated because on the left side we have a sum of 2 trig functions, right? Or 2 terms. On the right side, it is 1 fraction, but we also have a difference in the denominator. So you can think of it as, well, this has a sum, that has a difference, but that also has a fraction. Does that make sense? Let's see, we are on 6. Okay, so example 6. So once in a while, you might get one that's a little more complicated to get to make it look like the other side. So you'll probably have to work on each side, both sides, and get them each to a point where they look the same. Does that make sense? So you would change both sides, but just enough so that they look the same. Does that make sense? So that might happen on occasion, and this is one of those examples. You can also do this, verify. We have cotangent squared over 1 plus cosecant of theta, 1 minus sine over sine. So let me do one at a time. So here, let's say we worked on the left side. So this could be an option for you if you like keep working and somehow you just can't seem to get to the other side. You might want to try the double pronged approach where you attack both sides. So let's say on the left side, I start with that fraction. So it's cotangent squared over 1 plus cosecant of theta. And we're going to start by changing, since we have a cotangent squared, we're going to do Pythagorean there. Cotangent squared is actually equal to cosecant squared minus 1. Cosecant squared minus 1. And we would probably do that because we see that we have cosecant on the bottom also, so we want to kind of see where this goes. Because this is square, this is difference of squares. This is the perfect square, this is the perfect square. So we can factor this to cosecant plus 1 and cosecant minus 1 on the numerator. So we'll do cosecant plus 1, cosecant minus 1. The bottom stays the same, since it's just 1 plus cosecant, right? Doesn't have a square or anything. And then we can see here that this and this match up. So these will divide out. And I'm left with cosecant of theta minus 1. Let's stop there for that one. And now let's attack the right side and see if we can get to the same place. The right side was 1 minus sine of theta over sine of theta. Okay. So if you notice, if I'm trying now to get here instead, make it look like this, right? That's 2 terms, the difference of 2 terms. I do have a difference here, but I only have 1 term. So let me break this up into this fraction and this fraction. So that would be 1 over sine minus sine over sine. And this would actually be cosecant minus 1. Okay. And at that point we would see, oh, you know what? I'm able to get the left side to this, and I was able to get the right side to this, or vice versa. And that means they are equal. Okay. So this might happen. How do you know when this is going to happen? You don't really know. It'll be just from practicing and investigating. Because a lot of times with some of these verifying identities, you'll start working on one side and you're trying to get to the other side, right? But you might get in a dead end, or you might get lost in there somewhere. So then you decide, okay, well, I couldn't do it from the left side. Let me try the right side. And then you try working on the right side, right? You start kind of doing different methods on the right side, trying to make it look like the left side. And let's say you kind of keep getting into a dead end also, right? Keep getting stuck. But from working on the left side and right side, you start noticing in your scratch work, oh, wait, I was able to get to this point and this point on both, so I'll just do that. Does that make sense? But otherwise, if you can go all the way on one side, you would. Okay. So it's something you won't really know until you're actually doing it. All right, let's do one more on this one. This is 7A. This is a little trickier because of the 4th power. You're used to seeing that. So in this case, we want to start based on like what our formula sheet has and stuff. mostly just squares. So we want to start here because this is new, right? It's more complicated than our, based on what we've been doing. And see if we can get the right side. So our first goal is to break that down, right? Because we don't have any definitions or identities with the fourth power, right? All of our stuff is like squared mostly. If you look at your formula sheet, you'll see maybe some square root stuff as well, but no fourth power. So we'll break that down first. An easy way to break this down would be tangent squared times tangent squared, right? So let's start there. We got tangent squared times tangent squared. Now we get rid of that degree 4 there. And now we can, we have stuff that we know how to work with, right? Tangent squared, obviously, we work with that a lot. Pythagorean, you would do. We know we're trying to get like secant in there and stuff. So tangent squared is equal to secant squared minus 1. But I'm only going to change one of them because as you can see on the right side, we still have tangent squared in there, right? So let's leave one tangent squared alone. And we'll just change the second one. Secant squared minus 1. And this is just based on the fact that we can see where we're trying to go, right? And where we're trying to go has tangent squared, but also secant squared. And as you can see here, this times this is tangent squared secant squared. This times this is minus tangent squared. So it gives us the right side. Had we chosen the other side to start with, what would we have to do? So think about it, right? If we had started here, so we probably started with factoring tangent, right? Tangent, so factor that out to get here. And then notice that this is tangent squared to get here, right? And then this times this gives us this. So we could have also gone the other way. So that's how all of them are, since they're all equations. Technically, you should be able to go from left to right or right to left. It's just that sometimes it might be a little trickier to do it on one side only.